This video marks our first day of online learning, our first day of the Acid and Bases unit, and my fourth appearance on YouTube. Let's hope it works. So since we're just getting started on this unit, I just wanted to do a brief intro into some of the background information on acids and bases, sort of review and recall what you already know, and then introduce just the first couple of math type problems we can do here. So first step, reviewing our background information on an acid. You probably think of an acid as something that burns. If you got a definition previously, it probably revolved around the existence of hydrogen ions in a solution. And you might have also talked about the importance of pH levels. So if you're familiar with the pH scale, you know that acids are on the low end, between about 1 and 6, 7's neutral, water, and above that 8 to 14 are bases. And then if you talked about pH, you might have gone on to define pH as a measure of those hydrogen ions in the solution. And so that's a working definition. We're going to expand upon it a bit as we go through this, but that is a fine starting place to have in mind. Bases, similarly, and if thought of a base as typically some sort of cleaning solution, you may have also heard the term caustic used interchangeably with basic. One interesting base we're going to look at in a bit here is ammonia. It's a special base. We'll get to that later. And then your definition currently probably revolves around the idea of OH, hydroxide ions, in the solution. So the acid were the hydrogen ions, the bases are the hydroxide ions. And then, like I said, the pH of a base is on the higher end of the spectrum, above water, about 8 to 14 range. A real quick reminder of the naming conventions on acids and bases. These are 3 common rules. It's not all of the rules. There are a couple more naming conventions, but these are 3 pretty common ones that you should know. So if your anion ends in "ide," for example, if we had HCl, you may have written that out as hydrogen chloride. You put hydro in front of the anion name here, and then replace the "ide" ending with "ic," so you get hydrochloric acid. Same for these 2 rules. If the anion ends in "ate," if it had been hydrogen nitrate, then you just need the anion name and you replace the ending with "ic." So hydrogen nitrate would be nitric acid. If the anion ends in "ite," if you had hydrogen sulfite, then you have the anion name and you replace the ending with "ous," sulfurous acid. Bases are super easy. You just take the cation name, so the first element, and add hydroxide. So NaOH would be sodium hydroxide. Those are awesome. Here's a couple common acids you should be somewhat familiar with. Hydrochloric's a popular one, normally what people think of when they're trying to list a strong, dangerous acid. Hydrofluoric is what people should actually think of when they're trying to list a strong, dangerous acid. That one's terrifying. We won't ever touch it, but it's pretty powerful, so it's important. These 3 have several industrial applications. They're popular in problems as well. These 2 have more day-to-day applications. You'd encounter citric acid in citruses, acetic acid in vinegar. Here's some common bases. Again, appreciate how straightforward the naming conventions are here. And like I said, the special one. If you're looking at the formula for ammonia, you might be tempted to think that that's going to be an acid because of all those H atoms. You might think that when ammonia goes into water, it'll dissolve and separate from all the H's and have 3 hydrogen ions floating around and be very acidic. But what actually happens is that it attracts an additional hydrogen to it. So it steals a hydrogen from an existing water molecule. So the NH3 goes into the water. The surrounding water molecules will lose one of their H atoms to it. As a result, there are now OH molecules floating around. There's now hydroxide ions floating around because the water molecule that was there lost an H to the ammonia. So this NH3 then has the same overall effect that a base would have because it increases the amount of hydroxide ions. We'll look more at other bases that follow this pattern later. They're called Bronsted-Lowry bases, and yeah, we will discuss this more later. So you might be sitting in your house being like, is there really a bunch of hydrogen ions floating around in our acids? Because like hydrogen has one proton and one electron, so a hydrogen ion's just a proton, right? And that seems like it'd be incredibly unstable to just have a bunch of protons floating around. And you would be correct. That's not really what's happening. It's a convenient convention. It can be very useful for us. But what's truly happening is that some of those H ions are bonding with water molecules to make the hydronium ion. So they're not floating around as H plus by themselves, because if they were floating around in water as just a single proton, they're going to see a water molecule and they're going to see the two non-bonding pairs of electrons on the oxygen atom and be attracted to those. So they're going to form a bond with one of those non-bonding pairs and give us H3O. The overall effect is pretty much the same. It's still a positive ion. It's still floating around in our solution. There's still one extra H. This is just a closer depiction of reality. Here's sort of a way to visualize this. Here is our water molecule. We could talk about the concentration of H plus ions in it, as long as we recognize that those H plus ions have probably bonded with the water molecule to actually make a hydronium ion. We could still talk about the concentration of the hydronium ions interchangeably. In whatever ways we talk about the concentration of H plus, we can talk about the concentration of hydronium instead. And on the base side, still a bit more simple and straightforward. A water molecule is losing an H to make our hydroxide ions, and so we care about the concentration of this ion. So the pH scale is something you're probably familiar with. It tells us how acidic or how basic a solution is. And I just want to take a bit of a closer look at the pH scale today. The pH scale is a logarithm scale. So a quick look at logarithm rules just to remind you. Logarithm is just another way of writing an exponent relationship. So you've got your base, or your base. A logarithm equals an exponent. So since this logarithm equals 2, that'd be the same thing as writing base 10 to the second exponent. And then it equals this number that would be inside the logarithm. And we don't have to use base 10. We can use 4 or x or any number as our base, as long as we keep it consistent between the logarithm and the exponential form. So pH is a logarithm. That's what the little p in front of the H means. It means it's a logarithm of the concentration of hydrogen ions. So what we care about, hydrogen ions or hydronium ions, technically, the definition of pH says that it's the negative log, base 10, of the molar concentration of hydrogen or hydronium ions. In here, we'd be plugging in our molarity, so our moles per liter, our concentration of either of these ions. So to give you an example, in water, the concentration of these positive ions is 1 times 10 to the negative 7th moles per liter. So that's the number we plug in here in our pH formula for the molar concentration. So we'd get the pH is equal to the negative log base 10 of 10 to the negative 7th. Hopefully you can see where that would work out to 7. We would have the negative pH equal to the log base 10 of 10 to the negative 7th. That'd be like writing 10 to the negative pH is equal to 10 to the negative 7. And so our answer is 7. Here are a couple other problems for you to try. I'm going to talk about this one in depth, and then you can try the other problems on your own. So we want to know the pH of a solution that is 0.1 molar HCl. So 0.1 moles of HCl per liter. So the first thing we need to do is know the concentration of H plus ions that results. So we know HCl is going to dissolve in water, right? It will break apart in water. It will break apart into its respective ions. We'll put in HCl. Once it hits the water, it'll dissociate and we'll have H plus ions and Cl ions. Now, since these are 1-to-1, if we put 0.1 moles per liter in, we will get 0.1 moles per liter of H plus ions as they break apart. I hope that makes sense. We can't have somehow more H than Cl or more H than HCl we put in, because whatever we put in is just breaking apart. So if we put in 0.1 molar, that means we have 0.1 moles of hydrogen ions and 0.1 moles of chlorine ions per liter. So we can plug the 0.1 in for our molar concentration of H plus ions in our pH formula. We get the pH of this solution is 1. Very, very acidic. Here are a couple other ones to try. Same ideas. Here we're given a range of molar concentrations of hydrogen ions in stomach acid. We plug those two concentrations into our pH formula. We've got a range of the pH of our stomach acid. We can do the pH of milk. We are, of course, hoping this is close to neutral because acidic milk sounds horrifying. And look at that. It comes out to about 6. We plugged in either 0.000001 or 10 to the negative 6 into our formula. Our pH is 6. And we could do the pH of bodies of water, oceans, hoping this is close to neutral too, so that we don't have to worry about our skin burning off as we swim. Plug that number into our formula. We get a pH of about 8.5. Safe enough. Alright, so in those examples, we knew our concentration of hydrogen ions, and we found pH. But we could also go the other way, right? If given pH, we could solve for the concentration of hydrogen ions. Let me go back a slide. We could rearrange this equation to solve for this part if we knew pH. We can move the negative sign over. We'd have the log base 10 of our concentration equals a negative pH. So to rewrite that in exponential form, we would have 10 to the negative pH equals this concentration. Let me show you an example. So for example, if we knew our pH was 3, we would know that our concentration in that solution must equal 10 to the negative third, or 0.001. That's our concentration of hydrogen ions in this solution. It's just the pH, the same logarithm pH formula, rearranged to solve for concentration instead of pH. Here are a couple of examples for you to try. You can pause and try a couple in your notes if you want. Make sure you're able to get these answers. In all cases, we're doing 10 raised to the negative pH is equal to the concentration of hydrogen ions. Now it's one more step, but we could also figure out the concentration of hydroxide ions. Now pH itself measures the concentration of hydrogen ions. That's why it's an H here. If we had pOH, it would be the logarithm concentration of hydroxide ions. But pH is a more common measurement. So if we have pH, we can also go between and figure out either of these pieces. So to get pH being given OH, first we need to have the concentration of hydrogen ions. We can't figure out pH just from hydroxide because pH is based on hydrogen ions. So we've got two steps. First, we have to figure out this concentration based on this one. Now we will talk more about the reasoning behind this step and why it works later. But for now, just to get you the formula, what you do is you take what's called the K factor of water. That's defined as 10 to the negative 14th. Again, don't worry too much about that definition now. We'll come back to it. But we're taking this 10 to the negative 14th and we're dividing by the concentration of hydroxide ions, and that will give us the concentration of hydrogen ions. Then we can calculate pH just like before. So for example, if the concentration of OH was 10 to the negative 9th, then the concentration of hydrogen is just 10 to the negative 14th divided by that 10 to the negative 9th. Remember that when you divide powers of 10, you can just subtract these exponents. So negative 14 minus the negative 9. 10 to the negative 5th then is our concentration of hydrogen ions. So the pH of this solution is 5. This step was solved just like the previous slides. Again, here's a couple of examples for you to try. Remember that we have to fill out this column first. We have to take 10 to the negative 14th divided by these concentrations of hydroxide to get these concentrations of hydrogen, and then we can solve for pH. So here are those answers for you to compare to your work. Now, if we are doing things in the lab, we're probably not going to break out our pencil and paper and do these logarithms to calculate pH. We're probably going to try to measure it instead, and there are three basic ways that we can do this. You've probably seen or used pH paper before. It's a strip of paper, you dip it in your solution, it changes colors, and then you compare the color of your paper to a given reference spectrum of colors. And whatever color you find, that gives you a range of pH values. Now that has its place. It's super cheap, it's quick, it's easy, but it really only gives us a guess at the pH. It's not super accurate. There's lots of room for error, especially just based on your interpretation of the color. You know, you have to decide what color it matches most closely and kind of estimate where in that spectrum you think your pH is. So it gets you a good guess, but it's not very precise. We can use indicators, which are chemicals that change color at a certain pH, and we'll talk about those on the next slide. These are pretty good. They're not quite as inexpensive as pH paper, but they're still pretty affordable, pretty user-friendly, fairly easy, and they're pretty precise. They're pretty accurate. If we wanted the highest accuracy and precision possible, we could use a pH probe or other analytical equipment. This is incredibly accurate. They're well-calibrated digital devices, but they're also very expensive. So we will go with that middle ground and use the indicators. Like I said, these are chemicals that will change color when you get to a certain pH. So each indicator has a threshold value, basically, where if you get to that pH, it will change colors to indicate that. And so if you have a process, if you're looking for a certain pH, you can choose an indicator that is tuned to that pH. Here are some examples. This one up here is called bromethyl blue. As you can see, it starts yellow at the low pHs, so in the acidic range. It turns green at neutral, at water, and it is blue in the basic range. Methyl red's another, red to orange in the acidic range, sort of a gold at neutral, and yellow as we go more basic. This is phenolphthalein. This one's pretty useful because it has such a dramatic change here. We've got clear all the way up through neutral, no change, and then a really dramatic jump to dark pink when we hit the basic levels. Here are a couple other types of indicators. This chart shows you what range of pHs they measure for and what color change you would observe if you use them. So as you can see, you can really find an indicator for any pH range you're interested in. Alright, last idea for the day. When we were talking about hydrochloric acid, we mentioned that we know the concentration of hydrogen ions will be the same as the concentration of the hydrogen chloride we put in, because we know that those atoms are going to split apart in water. And that process of splitting apart in water is called dissociation. Now, every substance is going to have a dissociation constant that tells you how well it breaks apart in water. Now, if this is starting to sound like equilibrium to you, then you are on the right track. We will represent the dissociation constant for an acid as Ka. This is really just a specialized equilibrium constant. It's going to sound very similar. So the dissociation constant K for an acid A is the concentration of the possible products of dissociation, so the ions it could split into, divided by the concentration of the material that does not dissociate. So to give you an example, if we had the material AB, compound AB, dissociating in water, to make A and B ions, then our dissociation constant would be the concentration of the A ions times the concentration of the B ions, so our products, over the concentration of the compound reactants. We could take a logarithm of this constant, just like we did for the concentration of hydrogen to get pH. It would give us pKa. The little p in front of these values is indicating that we are taking a logarithm scale to it. So we can take the logarithm of Ka, the dissociation constant for an acid, or Kb, the dissociation constant for a base, and this number will typically be constant if temperature is constant. So our pKa would be the negative log base 10 of this dissociation constant value, the concentration of the products over the concentration of the reactants. Here's an example. Let's say we know that the pKa for hydrofluoric acid is 3. If you look it up, yes, it's a bit higher than that, but we're avoiding decimals here for easy math, so we'll just roll with that. And we also know that the molarity of the solution is 0.01 molar, 0.01 moles per liter. So our given information here is that we're putting in 0.01 moles per liter of HF. We know that the logarithm of the dissociation constant for it is 3, and we would like to know what our concentration of H plus ions is. So first up, we know that the pKa value is 3, so we know that the negative log base 10 of the concentration of our two possible ions over the concentration of our compound is all equal to 3. Now, we could also deduce that these two concentrations have to be equal, right? Because they're both coming from the HF. Every HF that splits apart releases one hydrogen and one fluorine ion. These concentrations will always be equal. We can't have an H split off without creating an F. So we know the concentration of HF. It went into our solution at 0.01 moles per liter. And we know that these two have to be equal, so we can replace this F ion with the hydrogen ion and rewrite this equation. The pKa is equal to 3 still, which is equal to the negative log base 10. The concentration of our products is rewritten as the hydrogen ion squared because we've replaced the fluorine ion concentration with an equal hydrogen ion concentration. So we know these numbers are going to be equal. We can do that since it's the same number going in here, divided by our concentration of hydrogen fluoride in the solution. Now we have everything we need to solve this for the concentration of hydrogen ions. We get rid of the log first by shifting back to exponential form, so base 10 raised to the negative third power, negative because we moved this negative sign over here. It's really easy to miss the negative sign, so make sure you always take note of that. Would be equal to this inner number, the concentration of hydrogen ions squared, divided by the 0.01. And now we can solve for this. Multiply both sides by 0.01 and take a square root to get a concentration of hydrogen ions. Finally, we can put this back into our pH formula. The negative log base 10 of that concentration of hydrogen ions gets us our pH value of 2.5. Like I said, this was hydrogen fluoride, hydrofluoric acid. It's a very low pH. It's very dangerous. It's just terrifying. So, anyway, that concludes the content for today. Hopefully that went all right. Let me know if you have any questions. All right. Thank you.